Hello and welcome to take a look at the e-help, how it is constructed. We're going to do reverse engineering here. We are going to pull it apart to see how it's built. We start with the electrics, take all the wires and everything apart because this is a unit under construction, and we go all the way back to the aluminum. First of all, we start with the electrics. This is the electrical diagram. This is a small unit, so it only got half the batteries. But basically, the speed controller here is the unit you see here. And here is the cables to the motor, which goes inside the boom, and here to the motor. The motor is a rewound motor for lower RPM, higher torque. The engine speed controller is fed by plus and minus, and the wiring harnesses to the batteries is fixed on the negative side, and on the positive side it is via switches. Here is the switches, and this is for safety and service, so you can disconnect the batteries from the speed controller. So when you disconnect here, it's safe. Batteries are 2 blocks of 7 cells each, 14 cells, that is 52 volts in total. So this is a 52 volt system. This specific unit, you can connect a expansion unit, so you double the range. This is the e-help student. It's a lightweight, quite small unit which push about 30 kilos for 10 minutes. Let's pull it apart. We start by disconnecting the motor and take away the boom, just for make everything more visible here. So let's disconnect the motor. Here is the bolt that connects the tail boom to the rest of the unit. Now it goes apart for transport. This is the battery module. Now the motor is disconnected. Usually this is fastened here. Here we can see the power supply to the speed controller. Normally these ones are insulated with shrink hose, but just for visible and to pull it apart, it's opened here now, and also all the wires are loose. The engine speed controller has an anti-spark function, which is actually it's called pre-charge, which takes positive voltage over an impulse switch that we usually have in this place, and it pre-charge the capacitors before we put on the main switches. This wire is the anti-spark, the pre-charge. Usually it's wired all the way over here and taking power from one of the batteries, this one, and via the impulse switch. Then you have the mains, the plus. It goes to this bus bar, which all the switches connect to the plus of the batteries. We can see this plus here. For this unit, it is from these 2 switches, which is this battery and that battery, and then you have the switch for the expansion unit when you want to fly double the range. Let's remove the positive connection here and then remove the speed controller. This is the Turnigy Deluxe 250 ampere speed controller. It has proven quite useful for the e-help, We never experienced any failure with it, and it can take in practical some 160 amperes without overheating. Yes, it's stamped 250 ampere, but that is with extremely good cooling, I think. Okay, now we look at the harness for the plus. Here we saw the plus coming from the main bus, this one. We can disconnect the whole plus harness like this. And here we see that this goes to the engine speed controller, and it comes from this collecting bus, which is this one. These three inputs to the switches are from batteries. That is from various batteries. This eHub student basically have got 2 battery banks fixed, and you can fly with an expansion unit when you want to. So this is the plus harness. Then you got the negative harness, which sits fixed all the time. There is no switch in between here. On this unit it's quite simple. It goes from the minus of the battery here, try to disconnect, and it goes to the minus of the battery over there. Then it is connected, fixed to here. What is left of the battery module now is only the aluminum frame and the insulators where the DC switches are fixed to. So there is an insulation between here. If you look at the battery installation now, there is this neat little neck, and the reason for that is to connect the charging plugs to here. These ones are connected to the charger. Same goes for the balancing connectors. They are fastened to this swan neck. So this is a useful thing for connecting the wires. Also notice that the aluminum frame itself is quite thick, 2 millimeters, and the type of aluminum is not aircraft quality. By reason, I don't want magnesium here. You want the weldable type of aluminum because it can take heat a lot better than aircraft quality. Here you see a gate for the wires, protective a little bit for flames with some aluminum. If we disconnect the batteries, if we remove the battery, we see the bay they are located. The battery can potentially burn. Here is 1/4 of a kilowatt of stored energy that can burst in 10-15 seconds. Everything dissipated in that short time. All the flames and heat are supposed to go up, so the airstream will remove the hot gases and also toxic gases. These flame protectors will protect the wires to a certain degree, and also this is quite sturdy thing for not getting a propagation to the other batteries. So the whole concept is that if you have a failure on a battery, just let it burn. And also another thing is the gauge on the wires. This is 10 millimeter industrial, very high quality wires. If you look at the battery, the gauge is a lot smaller, which means that this smaller gauge will act as a fuse. It will burn off someplace here and not there. If we remove also the other battery, we come to the bottom of the battery bay. Here we can clearly see how the two batteries are serial connected, so we get 14S. It's fully possible to fly a eHelp with 12S, which make chargers and everything more practical. 14S is a little bit too much because you need special engine speed controllers and also the chargers. So my friend Boris, he is now developing the 12S version, which is a total different RPM on the motors and everything. So it's a total new setup. This is the aluminum casing for the battery module and also the fastening for the tail. This bolt fits snugly in here. You will need this for the cables and also for a good alignment of the bolt. To fix it, it's just this pin. As mentioned, type of aluminum, something not burnable. You know, aircraft aluminum contain magnesium and it will burn, so it's better with industrial weldable type of aluminum. 2 mm is good. Make it quite sturdy, because if something bad happens inside here, you want it here and not damaging your harness or equipment. And also for taking up the physical forces, because here is pushing 30 to 35 kilos and everything is supposed to be transferred to the hang glider harness. The underside, except for this preliminary bolt, this is how it looks. It wears a little bit on the harnesses, but basically it fits anything. This specific one is supposed to fit to a T-Nex hang glider harness, so it's curved. The weight of this is, well, it could be a lot lighter if you wanted to, but I don't push lightweight on that one because it's the fire safety. You can make it super light with carbon fiber and any exotic material, but the day something bad happens, you want it to be like a Vietnam M16 gun, sturdy, and working in every situation. If you look at the system here now, here's the positive harness, the negative harness, one of the batteries, the other batteries, the engine speed controller, battery expansion unit. This is a spare propeller, a foldable propeller. There's a lot of discussions about propellers. Do I like foldable? Oh yes, they are fantastic, but they are very expensive, and carbon fiber will cut anything which it can slash to pieces. So, in practical, these wooden propellers from German vendor Berntsen are proven to be probably the most practical and best performance for eHelp. Bigger diameter, lower pitch, and some of the advantages with wood is not too expensive, and if it hits something, buy a new one. If it hits the keel, if you have not removed the keel of your hang glider and it hits, it's just go into toothpickers. Now we are going to look into the tail section. The pipe here is old hang glider tube. You double it a little bit, precision drilling, put the wires inside. Then you got the tail skid, basically just riveted with regular rivets. Put some wheel here because if you're on asphalt. Then the engine mount, it's a round plate which is supported by these angles, and this is a really lightweight version of this. The total weight of this unit, I'm not sure. We can put it on the weight scale and we can see it. Well, a little bit above 4 kilos. 4.3 kilos, I think. Okay, let's see what is the weight of each part here. This is the aluminum, pretty heavy stuff. 1.2, it's 1.3, it's not much. Then we put all the heavy stuff. This is about 2 kilos, I guess. We're now to 3.5. We put the other battery in. 5.3. The speed controller, all the heavy copper. We do like this. We are up to 6.6 kilos. So the eHelp student seems to be with a 4.5 kilo engine part, about 11 kilo. So for about 11 kilo you can fly a hang glider. That's not bad. Then some thoughts about the batteries we are using. You maybe noticed that this is the same batteries that you saw on the first videos in 2014. It is 25C batteries. These days we are up to 65 available. So this is really old technology. It actually do the job. And this one have lasted for quite many years. It's only 5,800 milliamp hours each. But it kind of work. So the owner of this rig, he will fly with these batteries and probably replace them with more modern batteries. And what is the more modern batteries? That is two different things. If you want endurance, you should go for the modern drone batteries. Many of the drones today have really high capacity. The milliampere hours are fantastic these days. So you can, for the same weight, get quite long endurance. The problem is if you want to flat start, not flatland, but flat start, because then you need a burst of energy to climb out in the takeoff safely, which you need a very high C rating. Even with 25C, these batteries combined can do a flat start with this one. However, the endurance, if you went for the drone batteries and maybe got quite much longer endurance, then usually the C rating is a little bit low, so that might be a challenge to balance that. If you can launch from a hill, so you don't need the really brisk takeoff performance, the drone batteries will be better. And also going for 12S means that you can go with easier chargers, more available batteries. So the 14S is more for flatland start. What is the consequence on the engine system when you go down from 14S to 12S? Well, the propeller will spin a lot slower. Not a lot, but let's say you lose 10%, which means in thrust quite a lot, 30%, 40%. So you need a bigger diameter. Instead of a 3412, you maybe need a 3614 to run the same system with 12S. But our eHelp system of 12S is absolutely something to look into, just for the practicality. High performance, 14S. All the connectors that is needed for the system should be made of these gold contacts, and you should put some work and skills how to solder them so that the connection are safe. They should carry quite a lot of amperes, and also air cooling of wires are quite important, because the amount of amperes that we put through these 10 millimeters wires are quite high, so air cooling over the whole system is quite important. You should not cover the whole damn thing. If you cover a eHelp, it can be quite dangerous, because the wires will not get sufficient cooling. So I have experienced that actually wires caught fire because it was too insulated. It should be close to some aluminum, because aluminum is cold and you got a cooling surface. And also, if you put enclosure over, the flames and hot gases could not escape, and then you get a really aggressive lithium polymer fire. It's much better that you just evacuate all the gases and it can dissipate its quarter of a kilowatt hour just out in the air in 10-15 seconds, and that's it. If you put it inside, it's a furnace. The temperature here will be catastrophic high, and God knows what happens. So for the safety of the system, you should do exactly the same as we do on board in ships. Many of you guys know that I work with full-scale ships, battery ships, and the way that we can make a 1000 kilowatt hour battery safe on board in a ship is that we have small battery modules, and the energy can be dissipated. If one of these batteries burns, there is no way to stop it. Just let it burn. Lithium polymer batteries. What is our experience with lithium polymer batteries? The 4 years we have been flying about 5 units of e-hopes. It's quite good. We have destroyed some few of them by taking the voltage too low. We have experienced then that it's puffing up and you can throw it away. But we have never experienced any fires. In the laboratory, try to short circuit. Okay, there is a little show. But basically we have never experienced any really bad things. The fuse in the system of e-help is basically the motor. If you overload with too heavy propeller, it will burn here. These wires are not capable of surviving the amount of power this thing is capable of delivering. So if you're overloading propeller wise in a takeoff in a hot day, you will burn the winding of the motor, and that's it. We have done many times and never actually overloaded the batteries or the engine speed controller. Okay, nail test of lithium polymer batteries. Okay, now we got a self-contained fire in a lithium polymer battery. Let's see what happens. Now we have assembled the e-help student. All the wires, everything is in place except for the pre-charge button will be here. A significant difference between the e-help student and the flatland start e-help is the throttle actuator. On the student it's remotely operated. It could be carried by the pilot himself, of course, but it could also be controlled by an instructor on the ground. The regular e-help has this wire thing, which is a little bit awkward, so this is a great improvement invented by Boris. Now a little bit about the charger. The charger for the e-help is this one, but this is the big scale 40 ampere, which can charge this thing in about 2 hours, 3 hours. It will take that time because you need to balance each and every cell on the battery. One thing about these big diameter direct driven setups, they easily windmill. So if this is let to windmill, it will be a huge air resistance. It's almost like a parachute. It's totally different when the propeller is stopped and it's stalled. Then the air resistance is not too much. So when it stops, it should be like this with actively actuated brake. Bam. Here the brake is not activated. Big difference. You don't want it to windmill. Thank you for watching.